Welcome back. Today we talk about polar coordinates. Just want to point out that Project 8 was assigned last class. It's not due for a little while, but hopefully you've already started working on it. Quiz 8 is happening next class, and it's on the material from 28, 29, and 30. Let's get started. We have a way to describe any point in the plane in terms of its x and y coordinates. In this section, we discuss a different way to describe points in the plane. First, a review of the Cartesian coordinate system or the rectangular coordinate system. So you've got some random old point over here, P, and we'll say it's at x and y. So what does it really mean, this number x? Well, x is just how far it is from the origin to the point, right? But it says here x is the directed distance between P and the y-axis, which is this distance, but it's the same as this guy. But that word directed is there because if x is negative, then I have to somehow indicate that x is negative. Distance is always positive. So directed is our way of saying, hey, it's okay if you have negative numbers in there. It just means it's to the left, or in the case of a y value, it's down, right? That -1 means down 1. And y is the directed distance. It's just the y value is this distance, which is the same as this distance. So it's the distance, directed distance between P and the x-axis. So nothing new there. What did the coordinates of point Q mean? So it means that Q is how far. So what does that √3 mean? Does the √3 mean how far from the x-axis or how far from the y-axis? So √3 is this distance here, right? So it's how far from the y-axis. √3 from the y-axis. And then the -1 is, I'll say 1 below the x-axis. Okay, so now we're going to describe a different way to talk about points. 3, we now define a new coordinate system called the polar coordinate system. So the picture says it all. We no longer have x and y axes. We no longer have an origin. We now have something called the pole, and we'll still call that 0, but it's not 0, 0. It's just plain 0. We do have the positive x-axis. We don't have the negative x-axis, and we don't have any y-axis. This guy right here is called the polar axis, so we're not going to call it the x-axis anymore. And then you've got some point out here that you're trying to plot. So here's how we're going to describe this point. We're going to give instructions as follows. We're going to say, okay, the distance between the point in question and the pole is r. So we tell the person that they have to go r away. But how would they know to go r in that direction as opposed to r in this direction, or r here, or r here, or r there, right? There's this whole actual like circle of points that are all the same distance away. This is kind of cool. And so we also have to specify the angle that we go. And that angle is going to be in standard position, meaning from the positive x-axis, the polar axis now, up to the ray that goes through our point. So armed with the two pieces of information, the how far from the pole and what standard position angle, that's enough to uniquely determine that point. So let's read a little bit in 4. In polar coordinates, we have a point called the pole, which is analogous to the origin in Cartesian. We only have one axis called the polar axis, but we may just continue to call that the x-axis. In polar, an arbitrary point P will be defined by two coordinates, r and theta, where r is the directed distance between the pole and the point P. That's telling you how far to go. And theta is the angle between the polar axis and the terminal ray on which the point P lies. So there's this line that goes forever, starting at the pole and going through P, and we just have to tell the person who's reading what that theta angle is. 6. Let's plot the following points on both sets of axes below. Okay, so the first one is P, which is r and theta. So r and theta is like your new x comma y. And just like you already have memorized that x always goes first, you now need to memorize that r always goes first. So what we're saying here is that the r is 4 and the angle is 130. So it says go 4 units away. Now 4 units away could be this point or any number of points along this circle. And in fact, that's actually why we call it r, because we're thinking of it as the radius of this circle out here. So which of these points on that circle should we be at? Well, we should be at the one that's 130 degrees. So it's kind of hard to read here, but I think this is a 135. And this other guy here is a 120. So our famous angles are on this picture. And 130 is not quite out to 135, so maybe we'll say it's something like right there. So let's put that guy in a different color. So here's the point 4 units away at an angle of 130 degrees. R always goes first. Okay, so if we wanted to plot that thing on the standard XY plane, the Cartesian plane on the right, well, it's still the same thing. It's still at 130 degrees, which we said is very close to 135. Now 135 is the one that's halfway. It's like perfectly in that second quadrant. So we're not going to quite be there. We'll be a little bit clockwise of that line. And we need to be 4 units away. Now 4 units away is not so easy to see looking at this picture, but we can see, for example, that this guy right here is the 3 line, and it's a little bit above the 3 line. And this line right here is the 3 line here, and it's a little bit left of that 3 line. So it looks like it's a little bit above 3 up, and I said left, but a little bit to the right of 3 to the of this negative 3. So maybe somewhere around here, 4 comma 130. I mean, it is possible to figure out exactly what the x and y coordinates are, and we'll see formulas real soon. But for right now, we're just kind of eyeballing it, and I just want to make it clear that the standard axes here are just superimposed right on here. And so that point right there is just in the same spot, just thinking of it in a different way. Okay, how about negative 2, 270? All right, so negative, I don't know what's going on there with that negative business, but let's think of it just as a positive 2. Okay, so positive 2 is this circle, and 270 degrees would be this point straight down right here, right? 270 degrees we know is straight down. But this is a negative 2. And so now I will tell you that negative, in terms of the r, just tells you to go the opposite direction. So this one down here would be positive 2 and 270. But negative 2 and 270 says go the other way. So here's negative 2, 270. And that one is just sitting at the 0.02 right here. Okay, so again, if the r is positive, which it will be in most cases, then you just go to the point as usual. But if the r is negative, then instead of going to the usual point, you go the opposite direction. So pretty much find the usual point and then go the other way. Seven, find the coordinates of 2 other points that land on point P. Okay, let's see here. So P was the red one for us. So let's mark that over here. So here's point P. So I want 2 other points that land right here on point P. Okay, so how about instead of saying 130 degrees, we say, why don't we go backwards? Instead of 130 degrees clockwise, what's the equivalent angle going counterclockwise to land on the same point? So let's see, 360 and 130 and subtract. So that's 230 degrees. So if we said negative 230 degrees, I think that would work. So like 4 negative 230 works. What if we say we're not really feeling very efficient and we want to do a complete lap for no good reason, and then we're going to come back and then land on the 130 degree angle? So if we do 360 plus the 130, and that will just zip us around, and 490 works. There's 4 and 490, so that's fine. In fact, how many different ways are there to describe this point? Well, there's infinitely many. You could zip around as many times as you want to. And in fact, there's a whole other infinite family of ways to describe this point where you would start with a negative 4. So what kind of an angle would work for a negative 4 here? Well, let's see. So negative 4. So I guess that would mean we'd have to tell the person to go, instead of 130 degrees, I think I need another color and then I'll erase some stuff. So instead of going 130 degrees this way, I want to tell them to accidentally get down here somewhere and then go negative 4. So what's that angle up there? Let's see. So it's 130 going that way, and I guess the other part of it must be like 50 degrees going the wrong way. Is that right? Because we need it to be, it's a straight line there, so 180 altogether. So if we do 180 minus the 130, we get 50 is the rest of that angle. So if we tell them to go negative 50 degrees, that just says go clockwise 50 degrees, but then go backwards along that black line, and that's the negative 4 is the backwards part. Okay, so I think we've got a bunch of different ways to write this answer. So my diagram's all cluttered, so I'm going to undo some stuff here. And we'll fill in some answers here. So one answer we gave was 4 and negative, what was it, 230. Or we said 4 and then zipping around one complete revolution and then some. Sends us there. Or, and then we decided to really go for it and give a third answer, -4, and then 50 degrees clockwise. 8, note the coordinates of a point in polar are not unique. Is this the case in rectangular? If we're looking at this point here in black, this guy, are there any other ways to describe this point in rectangular coordinates other than 0, 2? Is there another way to get somebody to land perfectly on this point? The answer is no. So in rectangular coordinates, they're unique. There's only one way to describe a point. That's a far cry from the way things work in polar. Not just, you don't just have one other way to describe a given point. There's infinitely many ways. And in fact, there's in some sense like 2 times infinitely many ways to describe a single point. Number 9, I'd like to be able to convert between polar coordinates and r theta and rectangular coordinates x, y. So we're going to fill in these formulas, but let's figure them out. So first thing to do is what? So let's take a look at this picture. We've got some x comma y, that's standard. There's your x, there's your y. And then we've got the new polar version of things. R is the directed distance, theta is our standard position angle. So first thing I'm going to do is look at this triangle right here. And I'm going to say there's a real famous theorem we can use because that's a right triangle. And the theorem is the Pythagorean theorem. So one thing we definitely know for sure is that x squared plus y squared is r squared. And so if we took square root of both sides, then lo and behold, we have a formula that tells us r is the square root of x squared plus y squared. Technically should be plus or minus. Personally, I always pick the plus for r, but you're welcome to pick the minus. You'll just have to then change your angle accordingly. Okay, so we've got that one. Let's focus on the theta business. Now I'm going to come in here in blue. I'm going to write, what am I going to write? Well, I'm not going to write anything. I'm just going to say that tangent of theta. We know that the tangent is the, let's see, what is it? Is it x over y? No, it's y over x. So tangent of theta is y over x. So if I wanted to find theta, then I would take the inverse tan of both sides. And we get theta is the inverse tangent of y over x. And those two formulas right there, I'm hoping kind of look familiar actually. If you go back and look, I think it was the last class. Let's see if we can find it. Okay, I found it. It wasn't last class, it was 2 classes ago. So let's just go back a few pages to somewhere where we did something 2 classes ago. It might be this. Yeah, so if we come down here and take a look, you see this formula says a squared is a1 plus a2 squared. Well, that's an awful lot like r squared equals x squared plus y squared. And then over here, it said tangent of phi, I think we changed that to a theta, was a2 over a1. And the equation we just wrote was that tangent of theta is y over x. And so it's exactly the same calculations that we did. But back here, we were doing it for this kind of funny, can we rewrite the sum of 2 different, like a sine function and a cosine function as a single sinusoidal function? And we ended up with those formulas, and lo and behold, they're back in different contexts. So let's come back here. And we've got, what do we have? So we have the rectangular to polar version. Now we need the polar to rectangular version. So let's do here in green. Let's go ahead and find the sine of theta. Let's go with cosine first. Cosine of theta. Okay, definition of cosine of theta. Is it x or is it y? It's x. But that was when we were in the unit circle. And so the more general definition actually had it divided by something. It's always x over r. So if you multiply both sides by r, we get x is r cosine of theta, which is our conversion formula to find x. If you know r and theta, plug into there r cosine theta, and that will give you x. One more color to find y. Let's go ahead and write the sine of theta. Definition, is it x or y? So this one is y, but that was only in the unit circle. In general, it was y divided by r. So multiply both sides by r, and we get y is equal to r sine of theta. Okay, so there are 4 very colorful equations that I want us to be able to use. So let's try using them. But these are the equations you use to convert. If you have the rectangular, that is, you know x and y, and you want the polar, the r and the theta, you use these 2. If you go in the other direction, if you know the r and the theta and you want the x and y, use these 2. Okay, so we'll begin here. Part A. Convert the following into exact rectangular coordinates. Okay, and there's a little diagram here to help us. So this is like polar graph paper instead of normal graph paper. So 1, negative 30 degrees. So let's go negative 30 degrees. So negative 30 degrees is here. And then we're going positive 1, so that means go in this direction. And that lands us, let's see, 30 degrees, and it lands us right there. So here's the point 1, negative 30 degrees. Okay, so in order to find the x and the y, well, we just have to use the formulas that we've got up there on the right. So we know x is r cosine of theta, and this is the r, and this is the theta. So r is 1 cosine of negative 30 degrees. You could type it in the calculator, but this one says exact, so I think that means we need the radical versions of things. So cosine of negative 30 is the same as cosine of positive 30, which is a, what is it, root 3 over 2. Okay, and then the y value is r sine of theta, that's in purple up above, 1 sine of negative 30 degrees. Okay, sine of 30 is a half, but sine of negative 30 is negative a half. Use your unit circle if that's not in your head. And so we're done. So that means that the point in xy land is really at root 3 over 2 comma negative 1/2. So does that make sense? Well, if you envision the x and y coordinates, you know, just like the x and y axes in their normal places. So root 3 over 2 you can type on the calculator is about 0.866, comma, and then negative 1/2, so negative 0.5. And if I asked you to just plot that point, well, let's see, you'd go 0.866, so maybe around there, and then down a half, and maybe, oh, yeah, it's right where it should be. Those are the coordinates. That's how you find the coordinates. Okay, let's move on to B. Here we're going to go into rectangular coordinates to 3 decimal places. So again, we have the r and the theta given to us. And we'll use the same formulas as before. So we go 2 cosine of negative 108, and then 2 sine negative 108. And we'll just use the calculator to get some decimals here. Okay, so the first one we said was 2 cosine of negative 108. Okay, and again, following my advice, make sure you're in the right mode. Radians is not the right mode for this problem. So we have that, and then same thing, but now sine. And so we have our 2 answers. So let's plot this point and see if it's reasonable, these 2 answers that we got. So negative 108 degrees. Okay, so let's see. This one right here, I think, is 105. So it's very close to that, just a little bit counter or clockwise of that. And we're going out 2. So we're on the 2 circle and just a little bit clockwise of the I can't read it here. What is that? 255 angle. Okay, and then does that jive with what we have from the calculator? So we'll just write down from the calculator that these are negative 0.618 and then negative 1.902. So already I like the fact that they're both negative, because if we look back at the point, we'll write this in standard XY land, 0.618 and then negative 1.902. Okay, so negative 0.6 and then negative 1.9, is that reasonable for the point? Well, let's see, negative 0.6 is like here and negative 1.9 is there. Oh yeah, it's looking pretty good. So again, that's how you convert from this kind of foreign r and theta land, polar land, into standard XY land. Okay, C says into exact polar coordinates where theta is in degrees. Okay, so if we're going into polar, then this must be x and y at the moment. Okay, so the r formula, it's up above, square root of x squared plus y squared. Negative root 3 is getting squared plus 3 squared. So square that negative root 3, it just becomes 3 plus 9 root 12. And then the theta is the inverse tan of y over x. Always, always, always. So inverse tan of 3 over negative root 3. Okay, I'd really like to type that in the calculator, but apparently we're not allowed to. So this must be one of our unit circle things, but we don't have anything on the unit circle with a 3 in it. So how about we rationalize this thing? That is to say, take the 3 over negative root 3 and multiply top and bottom by root 3 over 3. Let's see if anything good happens. So on the bottom, we just get negative 3, and on the top, I'll just write 3 root 3, and then we cancel. And the whole thing simplifies to just negative root 3 over 1. I'll put the 1 in there just because I know that it's a tangent, and tangent on my unit circle comes from y divided by x. So look at your unit circle and see if you can find an x and y coordinate where the point is 1 and negative root 3. Okay, so hopefully we found this point on the unit circle, and that point happens at 300 degrees. So this problem was really asking for inverse tan of, what did we say, negative root 3 over 1, which is on the unit circle at 300 degrees. Okay, so let's see if we can plot this point in XY land and then see if it gives us what we expect. So XY land, negative root 3 comma 3. Okay, so root 3 is around, what, 1.7. And so we're going negative 1.7 comma 3. Okay, so we can estimate that. So we go negative 1.7, so around there, and then up to 3. Again, you have to like imagine trying to make this circular grid square. So, so maybe someplace up here, negative 1.7, and then up to 3. So maybe around there. Okay, and let's see if that's anywhere close to what we're saying the answer is. What we think is r comma theta equals root 12, comma, and then 300 degrees. Okay, this is a problem. All right, so does the root 12 at least make sense? So how far might it be from the pole to this point? Well, let's see, root 12 is, you know, it's between 3 and 4. So do I buy that that blue line is something between 3 and 4 long? Yeah, that's reasonable. But 300 degrees is not reasonable. I would believe that 300 is maybe on the opposite side of this line, but it is certainly not up there in the second quadrant. So this is where we have to be really careful. I said look for a point where there was a 1 in the x and a negative root 3 in the y. But that was because I chose to put that negative sign upstairs, but couldn't it just as well have gone downstairs? The answer is sure. And so let's go ahead and tweak that, because apparently 300 degrees doesn't make sense in the scope of this problem. So let's fix that. Okay, so this equals, so I'm going to change my perspective and put that negative there in front of the 1. And then we'll just make that a positive there in front of the root 3, and then say, okay, 300 degrees doesn't make sense, but it's actually the angle in the second quadrant that we're looking for. And so what do we get there? Not 300, but was that 120? Okay, so that comes from the unit circle, and then, oh, that looks pretty good, actually. Looks like we're right around that 120 degree line, so that's reasonable. So you do have to be careful. You know, you can't just blindly use inverse tan, because there are always two angles that will work, and you got to make sure you pick the one that's reasonable. And so to find that, you got to plot the point. The other thing that I'll say is that here I've written something that is blatantly false. Inverse tan of negative root 3 is not 120 degrees. You can type it in your calculator if you don't believe me. Inverse tan has certain restrictions on its range, and inverse tan will never give you an answer of 120 degrees. So if you type it on the calculator, you'll see that it'll give you this answer, but it'll give you the negative 60 degree version of that answer. So regardless of what the calculator says, you got to make sure that you are based in reality. So always plot the point when it comes to picking the angle, because there's always two choices you could pick from, and you got to pick the right one. Moving on to 11, an equation in r and theta is called the polar equation, and its graph is called the polar graph. To sketch the graph of a polar equation, we can plot several points satisfying the equation and connect them. And so just like when you first learned how to graph in XY land, you started by making tables. That's what we're going to do here. So number 12, let's fill in the table with decimals rounded to the nearest tenth. Then we'll plot the points and connect the dots. We'll check our answer on the calculator. Okay. So r equals 2 plus 3 cosine theta is going to be some curvy looking thing here. No earthly idea what it looks like. It's the first time we're ever plotting something in polar land. But just like you can make a table with x and y, we're going to make a table with theta and r. Theta is the independent variable here. We'll plug in values of theta, turn through this calculation, and get values of r as a result. So let's do a couple of these. You could certainly do them by hand. These are all nice angles. They're all in the unit circle, and so you can do these calculations by hand. But since we're going to go with decimals anyway, and like root 3s and root 2s aren't very useful in terms of plotting, I'm just going to use the calculator the whole time. So for example, if I do 2 plus 3 cosine of 0, 2 plus 3 cosine of 0. All right, so I should be embarrassed to type this, right? Because cosine of 0 is 1, so this is 5. But you can put a 5 right there, and then I can just type the same thing in again, but now make it 30, and we'll get a decimal. What did we say we were rounding to? Nearest tenth. Okay, so this one would go to 4.6, and then we can do the same kind of thing here up at 60 degrees and start filling in. So I'll fill in these first 3 and then ask you guys to do some more. So what do we have here? 5, and then 4.6, and then 3.5. So pause the video, take a couple of minutes, plot the rest, or fill in the rest of the table, and then we'll plot the points together. Okay, so if you've spent the time making the table, I now want to show you the shortcut for making the table. You can come in here and you can type in 2 plus 3 cosine x. 2 plus 3 cosine x. That is not right. And then you can go into table set, which is second window, and go ahead and make it so that your table looks like this. So starts at 0. Delta table, I want that to be 30 degrees because we're increasing the inputs by 30 degrees. Make sure it says auto right there. And if you set it up like that and then do second graph to get the table feature, then you will see the table right in front of you. So we've already got the 5, the 4.6, and the 3.5, but this now very quickly tells you the rest of the numbers. So I'm going to copy in the rest of my table, but this is a nice way to use a calculator to shortcut table creating. Okay, so I've used the table on the calculator to get a table of values here. And now we're going to plot these points one at a time, going back to first principles. So the first one says go 0 degrees and then go out 5. So 0 degrees means don't go up here at all, but rather stay here and then just hit the point at 5. So our very first point is just right over here at 0 degrees and 5. And remember we were saying r and theta, so this is really 5 comma 0 degrees. That point there. Okay, the next one is at 30 degrees, and then we go 4.6. So we're going to have to estimate here. So the 30-degree line is marked. 4.6, well, there's the 4 circle, and there's the 5. There's a 4.5 circle there. So just a little bit out past the 4.5 circle. So 30 degrees and 4.6 is maybe there. And so what I'd like you to do is, well, let's keep going. Let's just do a couple more of these together because things get tricky when you are plotting negative r values. So the next one is 60 degrees at 3.5, and then 90 degrees at 2, 120 degrees at 1/2. Okay, and then things get funny. 150 degrees, but we go negative 0.6. So 150 degrees is this line right here. And so going out to 0.6 would normally be there. But instead of being on the 150 degree going that way, we actually have to go backwards. We've got to walk backwards. So the 150 degree line continues straight through to the 330 degree line. So we're actually on that line, and we need to be at 0.6 away. So the 330 degree line and 0.6 is just a little bit outside of that 0.5 ring. Okay, and then the next one is 180 and negative 1. 180 positive 1 would be here, but instead it's negative 1. It's backwards. It's actually out here. Okay, I don't know what crazy thing these dots are doing. I don't see any kind of pattern, but let's keep plotting. 210 and negative 0.6. So you go to the 210, but you go the opposite direction because it's negative 0.6, so I think it's there. And then 240 is at 0.5. 240 is at 0.5 is there. Okay, so I'm starting to lose track of which dots came first. So I'm going to start to, you could number them. You could say, all right, that was the first dot, that was second, that was third. I'm just going to start connecting the dots in the order that they appeared. So it went up here, and then it came in here, and then it came in here, and then I don't know what happened, but it somehow ended up there, and then here, and then here, and then here. And clearly, if you want more detail, you got to plot some more points. But that's what I've got so far, just connecting these things, not with straight lines, but with curvy things. Okay, so the last one we just plotted was 240 and 0.5. So let's keep plotting. We're now down here, 270, 2. So this is straight down and out at the 2 circle. And then 300, 3.5 there. 330, 4.6. And then finally 365, which is right back where we started. So let's continue just connecting the dots. Oh, look at that. Definitely never seen anything like that in terms of X and Y graphing. But apparently this is what 2 plus 3 cosine of theta looks like. R equals that thing. So it turns out you can graph this thing on your calculator. Now, I typed in y equals 2 plus 3 cosine x. And if I just look at the graph of this thing, let me see here. So we got to think about the window. So 0 to 360, I guess, is the right window here. But if I just look at this thing and then the y's apparently go all the way up to 5, and they do get negative. I'll just do negative 5 to 5. But this is just going to graph an ordinary cosine graph. I mean, it's just 2 plus 3 cosine. We could graph that. We know it looks like cosine. Amplitude is 3, and then bump it up 2. So that looks really nothing at all like this guy. So here's how we get the calculator to graph this guy. Go into mode. Come down here to where it says function. That's where we normally are. But there are actually 3 other options here, which probably you've never played around with. But one of them represents everything we've talked about today. We've been talking about polar. So scroll over twice. POL stands for polar. Okay, quit out of there. All right, nothing looks any different here. You can just do ordinary calculations as usual. But we're going to go into y equals and be very surprised. Because for the first time in our lives, it doesn't say y1 equals, y2 equals, y3 equals. It says r1 equals. Well, there's your r1. 2 plus 3 cosine theta. 2 plus 3 cosine. All right, so where do we find theta? Well, normally what you type in right here is x, right? For your whole calculator lives, you've been typing x there. Well, let's look at that button. That button says x, but it says a bunch of other things too. And one of them is theta. Okay, let's just hit that button. Not x. It knows that you mean theta because you're in the theta mode, the polar mode. Okay, so far so good. Let's think about the window. Okay, let's go into window. Oh goodness. Okay, so here it doesn't even start with x min, it starts with theta min. So we got to tell it the minimum theta, which we said was 0, and the maximum is 360. Okay, 0 to 360. That's fine. The theta step. Okay, this is a little bit of a balancing act. I'm going to put in, what am I going to put in? I'm going to put in 5. That's going to plot a point every 5 degrees, and I'll show you some of the pros and cons of increasing and decreasing that number. Okay, x min, well, why are there x's here when there's no x's here? Well, because we know that this is still the x-axis, even though we don't call it that. So how about we graph x min at -5 and x max at +5? And we can go by ones there. And then the y's, even though we don't call it that, are, you know, these numbers here. So we'll do -5 to 5 there, and that's fine. And then we're going to hit graph. Oh my goodness, look at that. And that's what we drew. It's looking pretty good, actually. So that's how you can graph things in polar land on your calculator. So I mentioned that I would talk a little bit about this theta step. So if you type in a big number here, like let's say we just type in 30 degrees, which is the theta step that we looked at here, right? What this is going to do is it's going to plot these points, exactly the points that we have here in purple. But the problem is it doesn't know to connect things with curvy stuff like we did. It's going to connect these things with straight lines, and it's going to be kind of jagged looking. Yeah, it's just not as realistic, right? You can see it's just plotting these 2 points and then connecting them. That's this first line segment. Then that point up there is this next one, but it just connected with a straight line. Okay, so the downside is that it's very jagged and not very realistic. But the upside, I don't know if you noticed it, but it graphed that really quickly compared to when we were doing it. I think we did every 5. So this is going to take a little bit of time to plot through because it's plotting many more points than we just did, 6 times as many points. So if you think that that's too blocky, I don't think it's going to get much better. But if you want, you can just change it to like every 1 degree or every 0.1 degrees. It's going to plot more points, but the downside is going to take longer. And so you can see it's going much slower. And we'll get a, and we know what this thing looks like already. But the smaller you make that theta step, the more accurate your graph. But the downside is that it takes longer to graph. So you got to find the balancing act between time and accuracy of the graph. It's still going, you just got to give it patience or be patient while it's doing its thing. Polar coordinates are also useful for describing circular regions, a slice of pizza, a frisbee with a hole in it, and these will be important in calculus. Let's see if we're done here, almost. Okay, so there is a long activity that follows. Again, give it your best shot before looking for the video of me going through it.